Hello friends, in this video I'd like to solve the following problem from Concrete Mathematics textbook, problem 31 from chapter 2. We wish to evaluate the following sums. One is k goes from 2 to infinity, zeta of k minus 1, and the second one is sum which goes from k equals 1 to infinity, zeta of 2k minus 1. Where zeta denotes the very famous Riemann's zeta function. So my hints for this problem, first of all, recall what exactly Riemann's function is. Well, it's defined zeta of s is by definition the following series, which goes from j equals 1 to infinity of 1 over j to the power of s. Then at some point it will be very important to exchange the order of summation and use Tonelli's theorem that exactly allows us to change the order of summation, and then use partial fraction decomposition. And also, I have not written it, but pay attention for sums of geometric progressions along the way. So give this problem a try and I will see you in a minute. Okay, so let's take our first sum which goes from k equals 2 to infinity, zeta of k minus 1. Well, by definition, this zeta function is an infinite sum which goes from j equals 1 to infinity of 1 over, well, j to the power of k minus 1. And let's now notice that if j equals 1, the first term of zeta function is just 1. So we can simplify our sum a little bit by summing just from j equals 2 to infinity of 1 over j to the power of k. Okay. Crucial fact, our summands are positive. And since they are positive, Tonelli's theorem allows us to freely exchange the order of summation. By Tonelli's theorem, we can freely change the order of summation, and I will do exactly that. I will first sum over j from 2 to infinity, and then I will sum over k from 2 to infinity of, well, and I will write 1 over j to the power of k. Okay, very well. And now let's notice the following. Here I have the second sum, I have a geometric progression, but starting from k equals 2. So this sum is, well, the first term of geometric progression. In this case is 1 over j squared over 1 over the quotient. The quotient in this case is 1 over j. Of course, this quotient is between 0 and 1, so this formula really holds. It's legal to use it. And now what we get here is just sum from 2 to infinity, 1 over j times j minus 1. And now it's time for partial fraction decomposition, because we have in the denominator we have a product of two binomials, and that means then we can split this, and you can do it in whatever way you wish, but I will maybe guess that the correct decomposition is 1 over j minus 1 minus 1 over j. You can do it by hand by setting that this equals a over j minus 1 plus b over j, and by comparing coefficients on both sides you will deduce that it's 1 and minus 1. Okay, and now let's do what exactly? Well, remember that this sum, infinite sum, it's just sum where capital J goes to infinity of what exactly? Of subfinite sum. Sum from 2 to capital J. Maybe write it in. You know what? Write it in. Pink, for example, why not? Okay. So it's 1 over J minus 1 minus 1 over J. Very well. And now it's just the matter of simplification. So we have our limit as J goes to infinity. And here, let's write this sum, you will see what's happening. If I put J equals 2, I will have 1 over 1. I will have 1, just 1, minus 1 over 2. The next term will be, if I put J equals 3, I have 1 over 2 minus 1 over 3. The next term is 1 over 3 minus 1 over 4. And so on. I hope that you see the pattern emerging. The last two summands will be 1 over J minus 2 minus 1 over J minus 1 plus 1 over J minus 1 minus 1 over J. And a beautiful telescoping. It's happening. Gone, gone. Everything is gone. Only the first and the last term are left. So we are left with 1 over 1 minus J, which is of course 1. So our first sum equals 1. Very well. The second sum is a bit harder, but not that much. Not that much. The second sum is sum goes from k equals 2 to plus infinity. K goes this time from 1 to infinity, zeta of 2 times k minus 1. Again, let's put from definition of Riemann's function, it's sum from j equals 1 to infinity of 1 over j to the power 2k, this time, minus 1. Again, if j equals 1, the first term of our inner sum is 1, so it can be simplified. K goes from 1 to infinity, j goes from 2 to infinity, 1 over j to the power 2k. Very nice, and now again our summands are positive, our terms are positive, so by Tonelli's theorem once again, we can freely exchange the order of summation. So I have sum over j, inner sum is over k, okay, and I have again 1 over j squared to the power of k, and once again I have a geometric progression. So I have sum which goes from j equals 2 to infinity. First term, if I put k equals 1, I have 1 over j squared, 1 minus, well, 1 over j squared. Is it right? Yes, it is. Simplifying, we will get 1 over j squared minus 1, but j squared minus 1 decomposes nicely into 1 over j minus 1, j plus 1. And now it's time for partial fraction decomposition. Again, you can do it by hand. and I will have 1/2 over j minus 1 over 1/2 j plus 1. And now our infinite sum is limit as j goes from infinity of a finite sum. J goes from 2 to j. And let's put, you know what, let's put 1/2 in front, and I will have 1 over j minus 1 minus 1 over j plus 1. And now I need a new page. And again, let's write first terms and let's see what's happening. Let's expand our sum. If I put j equals 2, I have 1 minus 1/2. No, sorry, 1/3. If I put j equals 3, I have 1 over 2 minus 1 over 4. J equals 3, yes. If I put j equals 4, I have 1 over 3 minus 1 over 5. Then I will have 1 over 4 minus 1 over 6, and so on. The very end will be 1 over j minus 1 minus 1 over j plus 1. But before these terms, there will be 1 over j, 1 over j minus 1, and here we'll have 1 over, let's see, j plus 1, j, here will be j minus 1, 1 over j minus 3, and so on, and so on. And let's see what's happening. Again, lots and lots of cancellations. Minus 1/3 plus 1/3, minus 1/4 plus 1/4. 1/5 will cancel with one of the terms inside our ellipsis. And again, everything will probably cancel. Wait, have I made a typo? Yes, I made. Sorry, there should be 2, because every time our indices differ by 2. So there should be 2. Minus 1 over j minus 1 plus 1 over j minus 1. Everything will be gone apart from the last two terms. So it's 1/2 limit as j goes to infinity of, well, let's see, 1/2, 1 plus 1/2 is 3 over 2 minus 1 over j minus 1 over j plus 1. Obviously, j becomes bigger and bigger, so this part vanishes, and we are left with 1/2 times 3 over 2, 3 over 4. And that is our second result. So all in all, our first sum equals 1, while other sum equals 3 over 2. And that's it. So as you have seen, Tonelli's theorem is very useful. If you don't know what to do with a double sum, try to exchange the order of summation, but remember, justify it. Either Tonelli's theorem, Fubini's theorem, or some other theorem. And yes, that's it. So thank you for watching, and I will see you next time. Goodbye.